Hello, I hope you are doing well. In this video, we consider some applications of systems of linear equations. We will solve some examples on polynomial curve fitting and network analysis. Okay, so let's talk about the first problem, polynomial curve fitting. Suppose that we have n data points, So, they are just points on the plane, okay? Just point on the plane. And we have x1, y1, x2, y2, and so on, xn, yn. The meaning of this is like you have a function y equal to f of x, right? And suppose that you don't know the function, but you know if x equal to x1, so the function value is y1. If x is x2, the function value is y2, and so on. This is kind of, you do some measurement, right? You do some measurement. And at x equal to 1, you measure, and you got y1. And at x equal to 2, you got y2, and so on. So, they are data points on the plane. Make sense? So if you have function of more than one variable, so let's say function of two variables or three variables, so you also have such problem. Make sense? So it will not be data points in the plane, but maybe in the space, and maybe not in three-dimensional space, but in n-dimensional space. Okay, so in this course, we just consider this example just on the plane, data points on the plane. All right, we don't know the function f of x. We need to recover the function. That's it. And of course, the easiest way, the easiest examples of such functions are polynomials, right? Because polynomials are very good. They are continuous. They are differentiable everywhere. And I would say they are easiest one, right? Among elementary functions. So the problem is we need to find polynomials. Let's say px of degree n minus 1. We'll see why we have n data points, but the polynomials of degree n minus 1, okay? Such that the graph of px contains the given data points. So you can imagine that you have some, data points in here. You don't know the function. Okay, that is one point, the second point, third point, and so on. Let's say the n points in here, right? xn, yn, x1, y1. You don't know the function. You want to recover that function, but sometimes you don't need the exact function. You only need the polynomial, such that the graph of your polynomial passing through this point. So basically, you use your polynomial to approximate the function in here. Does that make sense? So this is why we call like polynomial curve fitting, right? So let's say we need to find some polynomial that is the most fit, right, to the function. Does that make sense? Okay. So why n minus 1 in this case? Look at this. In order to determine a polynomial px, right, of degree n, let's say that, of degree n, so you need n plus 1 points or n plus 1 numbers. Why? Because the general formula of polynomial of degree n is a0 plus a1x plus a2x squared plus so on plus an x to the n. This is about, degree n, right? So you need 1, 2, 3, and n plus 1 points in here. Don't forget that we start from 0 to n. That means n plus 1 numbers. So we have n points, right? So that means we need to find polynomials of degree n minus 1. Does that make sense? So I need to find polynomials of the following form: a0 plus a1x plus a2 x squared plus so on plus a n minus 1 x to n minus 1. Okay? We have n data points. That's fine. I will plug x1, or let's say I will write in general. Okay, let's say x1, right? x1. I plug x1 and y1 into this equation because x1, y1 satisfies, the equation of the polynomial. Why? Because the graph of that polynomial, right, pass through that point. You see? So that means when you plug coordinate of this point into the equation of the polynomial, you have identity. So I have the following equation. The first equation, a0 plus a1 x1 plus a2 x1 squared and so on plus a n minus 1 x1 n minus 1 equal to px1, which is y1. So I will skip this, okay? I will skip this part. I just write, everything in here equal to y1. So we have one equation for the first point. That means if you have n points, you have n equations. Okay? So let me write it down. You plug x2, y2 into the equation, you get a0 plus a1 x2 plus a2 x2 squared and so on plus a n minus 1 x2 n minus 1 equal to y2 and so on. When you plug xn, yn into the equation of the parabola, you get a0 plus a1 xn plus a2 xn squared plus so on plus a n minus 1 xn n minus 1 in here and yn. And what is this? This is the system of linear equations, right? And variables are a0, a1, a2, and an minus 1. So this is n variables. You see, you have n data points, right? That correspond to n equations for n variables. So that makes sense, right? And if you solve this system, and if you can find a0, a1, a2, and an minus 1, so you plug all these coefficients, right, back here, and you get your polynomial. Okay, that is how we can solve such a problem. Let's consider the following example. We just talk about 3 data points in here. So we have 1, 4, 2, 0, and 3, 12. Okay, so we need to determine the polynomial px equal to a0 plus a1x plus a2x squared whose graph passes through these points. So right now we already know the form, right, of the system. So I can write directly the system. Okay, so I just plug 1 right here, 2 and 3 into the equation, and we have the following: a0 plus 1 times a1 plus 1 square times a2 equal to 4, which is y1. The second one, a0 plus 2 times a1 plus 2 square times a2 plus equal to 0. That is for second point. The next one is a0 plus 3 a1 plus 3 square a2 equal to 12. So you have the equation, the system right away. And of course, if you want, you can write, the system in the matrix form. Even, just forget about this step, right? Okay, we can write that in the matrix form as follows. 1, 1, 1 square, 4. 2, no, it should be 1, sorry. 2 square, 0. Again, 1, 3, 3 square, 12. You see that? Given, if you have more than 3 points, or if your polynomials is of the degree more than 2, so you still can use this form. Look at this. In general, I can write in the following way. For the first equation is corresponding to the first point, right? So I can write 1, x1, x1 square, x1 cube, so on, x1 and minus 1. In here you have y1. You see that? The second equation is corresponding to the second point. You have 1, x2, x2 square plus x2 cube plus so on. Oh, no, not plus, sorry. It's just, that just pausing here. So we have n x2 to n minus 1, and you have y2. And you have 1 in here, xn square, xn cube, so on, xn to n minus 1, and yn. So you may need to copy this, and each time when you have n data point, you just plug x1, x2, xn into this system. Okay, all right, so we have some system. We need to solve that. That's it, in order to find a0, a1, a2. So we know how to do that already, right? Let's pick one in here. That is the leading element, so I will use Gauss elimination and then Gauss-Jordan elimination. I will multiply the first by -1, add to the second, right? So I have the following one. If I multiply the first with -1, add to the second, I will get 1, 1, 1, 4 in here. I got 0 in here. I got 1 in here. I got 3 in here, and I got -4. Okay, so I hope that you can check each step yourself. And then I will make this guy become 0. I multiply the first row with the -1, and then add to the third row. Okay, I got 0 in here. I got 2 in here. Here we should have, I guess, 8, right? Because 3 squared is 9. 9 with -1 is 8. In here we will have 8. Okay, now we finish with this guy. We move to this guy, and we need to make this guy disappear. We need to multiply the second row by -2 and add to the third. That's it. So I write here the second row times -2, add to the third. I got 1, 1, 1 in here, 4 in here, and then 0, 1, 3, -4, 0, 0 right here, -2, I got 2 in here, -2, so I got 8, 8 with 8 is 16, right? Alright, so from here we already have row echelon form. I divide the third equation by 2, or just multiply by 1/2. So I have the following one, R3 times 1/2. I got 1, 1, 1 in here, 4, 0, 1, 3, 0, 0, 1, 8, and here I have -4. Now we will use back substitution, right? I will do the back substitution in here. I multiply this guy with -3, add to the second, and this guy with -1, add to the first. All right, let's do that. I have 3 multiplied with -3, add to the second row. I have 0, 0, 1 in here, that is 8. So I have 0, 0, and 0, -3, with the a is negative 24, right? 24 minus 4 is negative 28. Okay, I write negative 28 in here. And then the second operation is R3 times negative 1 plus R1. You add to R1. So you got 1 in here. Here I think I have 1, not 0. Sorry for this. And here I got 1, right? And here I got 0, 0, negative 1, I have negative 4, right? So the last step is to make this guy disappear by multiplying the second row by negative 1 and add to the first, right? So I get R2 times negative 1, add to the first. I got 1, 0, 0 here. This should be 24, right? In here I got 1, 0, 1, 0, negative 28. And here I got 0, 0, 1 with the 8. So this is my solution, right? This is for A0 because this is A0. This is for A1. This is for A2. So my polynomials look like 24 minus 28x plus 8x squared. And the graph of this polynomial passed through the given 3 data points. You see, this is how we can solve such a problem. It's pretty easy, right? Now let's consider the second problem, analysis of a network. So you can see on your screen, you have a graph, right? A graph in here with 5 vertices. 1, 2, 3, 4, 5. And we have some information on this graph. The first thing is this graph is directed. Okay, directed. What does it mean, directed? Directed means each edge of the graph has direction. You see, for example, between 1 and 2, right? So you have direction from 2 to 1. That means you don't have another direction, right? You know, just the flow just goes from 2 to 1. Similarly, you have from 1 to 4 right here, from 1 to 3, from 2 to 3, from 3 to 4, from 4 to 5, from 3 to 5, and then from 5 to 2. So, you know, it looks like very simple, right? But many things in our life can be described using graphs, like traffic, like gas, like cell phone system, cell phone network, or internet network. Many things can be described using graphs. Don't forget that. And you can imagine that, right? You have 5 points or 5 cities, let's say that. And each time, you know, you go from city 1 to 4, and then, you know, 4 to 5, and then 5 to 2, and so on. So you have a network, okay? And we need to make the system, you know, valid. What does it mean? That means you need to find x1, x2, x3, x4, x5 in this case, so that, you know, every edge on this graph is compatible to the capacity of them, okay? Like this. What does it mean? That means, you know, when you go from 2, right, from 2 to 1, so this is, the capacity is 20. That means you cannot, you know, go higher than that. Does that make sense? So they asked us to set up a system of linear equations to represent the network in this figure. And then we need to solve the system. That means we need to find x1 in here, x2, x3, x4, and x5, so that the graph makes sense. The graph is valid. The network is valid. Okay, so how to do that? The network is valid is a good one if the total of input is equal to the total of output. So I can write here total of input equal to the total of output. So what does it mean? Look at the first vertex right here. So you have just one input right here with the capacity equal to 20. You see this? But you have two outputs. That means sum of two outputs should equal 20. Does it make sense? So I will consider each vertex and write one equation for each. In this case, you have 5 vertices, so you have 5 equations. All right? So let me write here for the first vertex, I have x1 plus x2 equal to 20. Okay? For the second one, I have one input x4. You see? I have one input x4 in here. But I have two output, 20 and then x3. Okay, so I can write 20 plus x3 equal to x4. That is for the second one. Similarly, we can move to the third one. For the third one, I have two inputs, x2 plus x3, and two outputs, that is 10 plus 10, which is 20. Okay. For the fourth one, I have two inputs, that is x1 plus 10 equal to x5. And for the last one, I have 10 plus x5 equal to x4. You know, I don't want to skip step, right? I just try to write out all equations and then let's rewrite this system. Okay, let's rewrite this system. Okay, so the system has 5 variables. We can rewrite it in the following way: x1 plus x2 equal to 20. For the second one, I can write x3, or I can write negative x3 plus x4 equal to 20. How about that? So I just move x3 into this side, right? The third equation looks like x2 plus x3 equal to 20 again. The fourth one looks like x1 minus, no, negative x1 plus x5 equal to 10. I just want to keep positive numbers over there. And then the last one looks like x4 minus x5 equal to 10. Okay, now we can write the matrix form of this. The matrix form of this. So I have 1, 1, 0, 0, 0. In here I have 20. Next one I have 0, 0 in here. Negative 1, 1, 0. I have 20. Second one I have 0, 1, 1, 0, 0. Again 20. Here I got negative 1, 0, 0, 0, 1. I got 10 in here. Finally 0, 0, 0, 1 and negative 1. And that is 10. So you have such system. Solving this system, you can find all values x1, x2, x3, x4, x5 so that the network is valid. Okay? Alright, so let's do this. I start from 1 in here. I have 3 zeros in here, which is good. I have only one negative 1. Perfect. And I just need to add the first two to the fourth, right? So I write R1 plus R4 in R4. I just copy the first row, 0, 0, 0 in here, and 20. Okay, the second row look like this, 0, 0, negative 1, 1, 0, and 20. The third row, 0, 1, 1, 0, 0, 20. The last row is 0, here I should have 1, 0, 0, 1, and 30. So 0, 0, 0, 1, negative 1, and 10. You see? All right, now we already finished with this leading element, but here we have 0, so probably I need to interchange, right? I need to interchange rows in here. Maybe you might interchange the second and the third row. Okay, let me write here. I interchange the second and third row, so it's long a little bit, but I hope it's okay. We need to solve this to the end. So I got 1, 1, 0, 0, 0 in here, and then 20 in here. Okay, I have 0, 1, 1, 0, 0, and 20 in here. The third row is 0, 0, negative 1, 1, and 0, and 20 in here. So I would like to save some time. So, you know, between this guy and this guy, I want to make this guy become 0. Right? I just multiply this row by negative 1 and add to the fourth row. So I'll do that right here. I got 0. I got 0 in here. Negative 1, I got negative 1. And I have 0 in here. I got 1 in here. And I got 10 in here. And then 0, 0, 0, 1 and negative 1 and 10. All right. So I hope it's not very confused. Anyway, we already got what? 1 in here. So we have negative 1 in here, right? Okay, now I can multiply, you know, the third row by negative 1 and add to the fourth row. Agree? So if I do that, I have the following. Let me write in here. So I get 1, 1, 0, 0, 0. Here 20, 0, 1, 1, 0, 0, 20. 0, 0, negative 1, 1, 0, 20, 0, 0, 0 in here, here negative 1, here is 1, right? So here you got negative 10, 0, 0, 0, 1, negative 1, and 10 in here. Okay, so if you pay attention, we are almost there, right? These two equations are the same, right? You just multiply the fourth by negative 1 and add to the last. So the last equation disappears. Does that make sense? Disappears means, you know, you will get 0 in here and 0 in here. And of course, 0 in here. So basically, you have the following row echelon form. Let me skip that step. I hope you can catch that, right? I will just erase this. Erase this, erase this. I replace this guy by 0, 0, 0. That's it. This is the row echelon form. So you see that, you know, the system has infinitely many solutions. Why? Why? Because, you know, we have 4 equations, right? But 5 variables in this case. And it's obvious that the system has solution. That's the first thing, because if we remember the number of non-zero rows in the coefficient matrix is 4. That is also the number of non-zero rows in the augmented matrix. So the system has solution. And since the number of equations is 4, but we have system in 5 variables, so it seems like we have infinitely many solutions. But let's solve this, right, to the end, and we'll see. I can write, let's do one more step, because we need to get reduced row echelon form, okay? So I will multiply, I just add this row to the third row, because I have negative 1 and 1 in here. How about that? Okay, and then I have the following one. 1, 1, 0, 0, 0, 20, 0, 1, 1, 0, 0, 20, got 0, 0, negative 1, 0, 1 in here, and 10, right? The fourth one is 0, 0, 0, negative 1 and 1, negative 10. Okay, So we finished with this. Now I move to this guy. I just add the third to the second. So when I add the third to the second, I got the following one. 1 1 0 0 0 in here, and then 20. I got 0. I got 1 in here, 0 0 and 1 in here, 20. 0 0 negative 1 0 1 10 0 0 0 negative 1 and 1 negative 10. Okay, so we need to do one more step. Because we still have 1 in here, right? We want it to become 0. I multiply the second row by negative 1 and add to the first one. But let's see, we are correct or not. I think we are wrong in this when you do this step. So this should be 30. Sorry, it should be 30. So this should be 30, right? Oh, okay. Now let's multiply the second row by negative 1, add to the first, and I hope we'll finish this pretty soon. I got 1 in here, 0 0 0 negative 1. Okay, so I will not forget this. I get negative 10, and then 0 1 0 0 1 30 0 0 negative 1 0 1 10 0 0 0 negative 1 1 and negative 10. Oh my goodness, we already have the reduced row echelon form. Okay, now we need to solve this, and of course, you have 1 free columns in here, right? Because we have 4 leading elements in here already. The only one is this guy. So I will go back, right? So if I denote this by the way, this is for x5, because that is the 5th column, right? For x5. So from this equation, from the 4th equation, I have, x4 equal to x5 plus 10, right? And then move to the third one. I have x3 equal to x5 minus 10, right? And then from the second equation, I got x2 equal to 30 minus x5. And then from the last one, I got x1 equal to x5 plus minus 10. And of course, x5 is free variable. So your general solution looks like you just compile everything. x5 minus 10, 30 minus x5, x5 minus 10, x5 plus 10, and x5, where x5 is an arbitrary real number. Okay, so that means, you have infinitely many variants, right, for this network. And all those variants can be described by this formula. Sometimes as systems, right, sometimes you don't have any solution. Does that make sense? So it really depends on the network. Sometimes you may not find, a such network, because, the corresponding system does not have solution. Sometimes you have infinitely many methods, right? Or sometimes you have a unique solution. It really depends on the network and its system. Okay, so given that in this video we do a lot of computations, but I hope that the video is clear enough, and the examples are also. So if you have any questions, just feel free to let me know. Okay, see you in the next video.